Alright, hello everyone. So today we're going to talk about chapter 3, and so essentially how the course is structured is the first two chapters are differential equations, so continuous models, and then chapter 3 and 4 introduces difference equations, which are basically discrete analogs of differential equations. Okay, and so the first thing I want to start off by saying is just illustrating what the difference between discrete and continuous is. So if we have a function, a discrete function, say it's a discretized sine function, this function will only exist at discrete points. So it'll only exist at discrete points. Okay. And then if we made it continuous, it would then, didn't draw that particularly well, but it would basically, the solid line that connects the dots would be the continuous function, and the discrete dots, and the dots would represent the discrete function. And so a good example of what discrete and continuous, or good illustration of what discrete and continuous is if we think about shoe sizes. So shoe sizes can be, say, 8, can be 8.5, can be 9, but you can't get, say, 8.13 shoe size. But your foot size can be any length. Your foot size can be 20 centimeters, it can go 20.135 centimeters. So basically, shoe sizes are then discrete and foot sizes are then continuous, in the sense that foot sizes can take on any value. So there's no value in between, so size 8 and say size 9. There's no value between here that a foot size can't take. But a shoe size can't take a point here, it can only take 8.5, for instance. And the point is that discrete doesn't necessarily mean integer or whole number like 8, 9. It can be 8.5, but discrete just means that there are gaps in the representation. So same as is currency. So there's a gap between 1 cent and 2 cents, so you can't have 1.5 cents. So even though it's a percentage of a rand, so 1 cent is 0.01 rand, so it's not integer, but there are still gaps in going from 1 cent to 2 cents. So currency is discrete. Okay, so that's just kind of a quick idea of, or hopefully a clarification of discrete and continuous. So essentially what we're doing here is we're introducing difference equations. So difference equations are the discrete analog of differential equations. And, well, what do we have? So we have an ordinary difference equation is an equation relating two or more variables of an unknown discrete function with one independent variable. The equation represents a condition that must be satisfied by the unknown function for all the values of the independent variable. So all we're saying is that there's some unknown function which we're looking for. This is the solution to our difference equation, and it must satisfy the difference equation at all points. So a good example here, xn plus 1 equals 1.02 xn. So we say that xn plus 1 is equal to 1.02 xn. So the value of x at the next time step, or the next point in whatever n is measuring, let's say it's time. So we could say that the amount of bacteria tomorrow at n plus 1 is going to be 1.02 times the amount of bacteria today. Okay. And so if x1 is equal to 1, x2 is going to be 1.02. So that's how much there is today, and that's how much there is tomorrow. Okay? And note that xn could take on any value. So xn is continuous in the sense that it can take any value, not limited to, say, integers, right? So we're talking about an amount of bacteria. It could be any amount of grams. But n is discrete, so we can't measure what x at 1/2 is, right? Or what 3/2 is, right? We don't know what this is, and this doesn't make sense. So the difference equation is defined on discrete steps, n going 1, 2. So we'll say here n equals 1, 2, all the way up to some number. Okay. So, so that's an illustration of what a difference equation looks like, okay? And we said n equals 0, 1, 2, all the way up to some other number n, and that should be a different n. So solving of the difference equation is the process of determining the most general form of an unknown function appearing in the difference equation. This function is called the general solution of the difference equation and will always contain a number of arbitrary constants. Okay, so it's very much analogous to the differential equations that we've seen, and the processes are quite similar. So the fourth point here that we need to note is the order of the difference equation is equal to the number of intervals involved in the equation. Okay, so this example here, xn plus 1 and xn. So the number of intervals involved is just going from xn plus 1 to xn. So there's only one interval, so it's first order. Okay, and we'll see some examples later on and illustrate different orders of difference equations. A linear difference equation is one which the dependent variable appears at most once in each term of the difference equation. So there's no product terms. So we couldn't have, say, xn plus 1 times xn. That would make it nonlinear. Okay? So xn plus 1, so each one of the dependent variables appears only once in each term. And here's a general form of the difference equation. And this form here, if 5t on the right is 0, then it's said to be homogeneous. And we can double check that using the same kind of rule. So we say that if we replace xt, so if we replace the tth term in the difference equation by some scaling, k times xt, and it doesn't change the result of the equation, if it remains unaltered, then that equation is said to be homogeneous. And this typically happens when 5t is 0, but it can be verified using this technique, and it's exactly the same process that we saw for differential equations. And finally, the coefficient of any difference equation is the part of the term that does not involve the dependent variable. So in this form here, f0t is the coefficient, and you can see that it doesn't necessarily need to be constant. It can be a function of this other term t. It just mustn't be a function of x. Okay. So discrete functions. So here are some examples of discrete functions and what do they look like. So I've got my mathematical notebook here for chapter 3, and let's see what do these functions look like. So first example, we say that yk is a discrete function that's equal to 24 times 3/4 times k. So as k increments, I'm going to be taking 3/4 to the power of higher numbers. So 0, 1, 2, 3, 4. So expect this to decay because 3/4 is less than 1, and a number less than 1 to the power of to higher powers will get smaller and smaller. And you can see here what I've done is I've just computed the series. Sorry. So here 24, 18, so 3/4 of 24 is 18, 3/4 of that is 13.5, 3/4 of that is 10.1.25, and so on and so forth. Okay, so the sequence gets smaller and smaller and smaller, and it looks like this. So it's only valid at these points here. So k equals 0, k equals 1, k equals 2, k equals 3, k equals 4. And if we were to interpolate that or connect the dots, it would look like this. And we see we have a decreasing function. Okay. Similarly, the second example we have is yt equals 1.2t. Okay, so t again is discrete. T equals 0, 1, 2, so on and so forth. And as we see, as t increases, 1.2 is going to get bigger and bigger, and we again see that the solution grows. Right? We note that because 1.2 is bigger than 1, as I take this to higher and higher powers, this number is going to get bigger and bigger and bigger, and so the solution is going to grow. Right? And again, you can see here this is a series, so it's 1 is the initial condition, or t equals 0 is 1. 1 times 1.2 is 1.2. 1.2 times 1.2 is going to give me 1.44, and so on and so forth, and this is going to grow. And you can see here, if I connect the dots, that's what it looks like. But the discrete solution, or the discrete function, is only valid at these discrete points. Okay, so example 3, yk equals 2, so it's a constant function. You can see here the solutions for k equal 0, 1, 2, 3, it's all just 2, and it looks exactly as you expect. It's just 2 for all values, and if we connect the dots, it looks like. And then finally, if our y of t is cos, so it's basically a discrete cos function. As time steps, we can see we get this cos function out. at the bottom there. Okay. So that should all make sense. Hopefully it's not too foreign. It should look relatively normal. And then there are a couple of exercises for you to do in the notes where the notes just ask you to sketch these functions, and you can do that. Try to do it by hand. These notebooks are on Sakai, so you can have a look at those solutions there if you get stuck. But it should be a relatively straightforward exercise. So these are just exercises going through. Right. So section 3.3. What we're going to do is classify these difference equations. So the first example is this one here. So y r plus 2, so this r plus 2 is the interval, so it's r plus 2, so it's two steps ahead, minus 2y r plus 1 plus 3y r. Okay, now this might look like y double dash minus 2y dash plus 3y, but it's not quite that. Okay, so it is a different beast to a differential equation, but it does have this kind of familiarity. So this one here, it's linear because each of these terms only appear once. Each of the dependent variables y only appear once in each term, so there's no multiplication of y's. The r does appear as r squared, but we don't care about the r because it's independent. It's the independent variable. It's second order because r plus 2 to r plus 1 is 1, and then r plus 1 to r yr is the second interval. So there are two intervals, so it's second order. You can also say, you can subtract r plus 2, say r plus 2 minus r gives you 2, and that's the, so take the highest order and you subtract from the lowest order, and it'll tell you the order of the equation. Okay, and we'll see later on an example of that. And it's non-homogeneous because the right-hand side is not 0. And we can verify that by replacing y with k times y, and you'll see that it doesn't give you the same equation. So the second one here, r plus 3 minus r is going to give me 3, so it's third order. It's linear because y, the dependent variable, only appears once in each term. Even though there's an r times y here, we don't care about the r. And it's homogeneous because the right-hand side is 0. We can also double check that by replacing y with k times y, and we'll see that the equation remains unchanged. Third example is nonlinear because we have this product here, y times y, yr times yr plus 2. So we have this term here contains two dependent variables, yr and yr plus 2. And this term here is also nonlinear, so we have yr minus 2 to the power of 3, so it appears 3 times in that term. It's non-homogeneous because the right-hand side is not 0. And it's fourth order because the highest term is r plus 2. r plus 2 minus r minus 2 is going to give me 2 minus minus 2, so 2 plus 2 is 4, so it's fourth order. So the difference from the highest to the lowest is 4. Okay, hopefully that makes sense. The next one is linear, so y appears, so the dependent variable only appears linearly in each of these terms, so it only appears once in each of these terms. Even though there's an r squared and an r factorial, it's still linear because we don't care about the r. It's ninth order because r plus 5 minus r minus 4 is going to be 5 minus minus 4 is 9, and it's non-homogeneous because the right-hand side is not 0. Okay. So hopefully that makes sense, and there's an example for you. Actually, I think that's all the examples. Okay. So, moving on, let me go back to the notes quick. So the notes say, so you can sketch these, classify those, which we've done. Okay, so solving these difference equations. So there are three methods. First is by reasonable guessing. This is similar to what we've done before, where we take what's called an ansatz, or we take the form using the eigenvalues and get a general solution. Second method is what's called the direct method, and this involves looking for a pattern. And this often is the method we use for nonlinear difference equations, and sometimes it works, sometimes it doesn't. And the third is using a computer, and essentially what difference equations are numerical methods for differential equations. So they're we can write a computer program and just simulate the solution for as long as we need to, and essentially calculate the update rules. And hopefully that makes sense, and we'll see a bit more of that in the labs. So let's do an example. The first example is, I'll do it here. So we have yk plus 2 minus 2yk plus 1 plus 5yk. Okay, and so this can be found in the notes on the bottom of page 6. So there are a couple of examples for you to try. I'm going to do this one. And so we have a second order linear difference equation. And so the first thing we're going to do, as we would have done for a differential equation, is write down a characteristic equation. So we write down lambda squared corresponding to this term, minus 2 lambda corresponding to this term, plus 5. So that's our difference equation's characteristic equation, lambda squared. We can then, so trying to factorize this, I think we're going to have some trouble. So we can write down lambda 1 and 2 is equal to minus b plus or minus the square root of b squared minus 4ac. This will be minus 20. So I can see it's going to be imaginary. B squared minus 4 root square root of b squared, sorry, it's not 4 squared, it's just 4, all divided by 2. This gives me 1 plus or minus the square root of 4 minus 20 is going to be minus 16, and that is minus 4 squared, so this is going to give me 1 plus, this is 4 squared, so this should give me I4, unless I'm mistaken. Okay, so 1 plus or minus I4 on 2, so this is going to be 1 plus or minus 2i. Okay, so we see we have two distinct complex eigenvalues, so it's 1 plus 2i and 1 minus 2i. If you have a complex eigenvalue, the complex conjugate of 1 is always going to be the other eigenvalue. So complex eigenvalues always appear in pairs, and that's what they look like. Okay. Now, the general form of the solution we were looking for is yk equals a lambda 1 to the k plus b lambda 2 to the k. So this would be a into 1 plus 2i to the k plus b into 1 minus 2i to the k. And this form is fine by me. I prefer this form, having the complex eigenvalues and they appear as they do here. The notes do try to write it in terms of sines and cos, and basically it's all in the notes. There's this example on page 6. You can work through it if you like. They write the complex eigenvalues as a pair of sine and cos, and you're welcome to do that as well. Either way will get you to the right answer, but I prefer this way. I think it's a lot easier, and it's a lot more transparent in terms of I can see that this is the eigenvalue and this is an eigenvalue, rather than having to decipher it as it appears in the notes. In any case, so that's the general equation for a second order difference equation. So it's really straightforward. Calculate the eigenvalues, write it down in the general form, and there it is. And it's very similar. So instead of having e to the lambda x or e to the lambda t, we just have lambda to the power of k. And so there's this analogy between e to the lambda t and lambda to the power of k. So this is in the continuous case, and this is in the discrete case. Okay. So next example is going to be a non-homogeneous equation, and so we're going to do that. And we have, what do we have? We have y k plus 2 minus 3 yk plus 1 minus 4yk equals 5. So we see it's non-homogeneous because of the right hand side. And so this is example 1 on page 7. So first thing we do, write down the characteristic equation. We can factorize this as lambda 4 times 1. I'm going to say minus 4 of those plus 1 of those. So minus 4 plus 1 is minus 3. Minus 4 equals 0. So this tells me that lambda 1 is equal to 4 and lambda 2 is equal to minus 1. Obviously which way around you write them doesn't matter. Okay. And so the general solution, yk, and you can denote this as a general solution, maybe a g there, is equal to a, some constant, 4 to the power of k, plus b times minus 1 to the power of k. Right? So this term is going to grow as k increases. Right? So this term is going to kind of exponentiate, grow up and increase as k increases. And this term here is going to oscillate. Okay, so minus 1 to the power of 1 is minus 1, minus 1 to the power of 2 is 1. So we have minus 1, 1, minus 1, 1. So you can see it'll oscillate. So this behavior will be growing and oscillatory in nature. Now for the particular solution, so the particular solution for yk should be in the form of the right hand side. So we just consider it to be some kind of constant. So let yk equal some constant little a. Then yk plus 1 is going to be that same constant, and yk plus 2 is going to be that same constant. That's for the particular solution. Now I'm going to take these three equations and plug them back into my original equation, and I'm going to get a from the first term minus 3a from the second term minus 4a from the third term must equal 5. So I have a minus 3 is going to be minus 2, minus 4a is going to be minus 6a equals 5. So a is minus 5 on 6. So our final solution is yk equals a 4 to the k plus b minus 1 to the k minus 5 on 6. Okay. A 4 to the k plus b minus 1 to the k minus this particular solution minus 5 on 6. So again, you can then substitute in k plus 1 here, k plus 2 here, substitute those back into the original equation at the top here, and see that this solution does indeed satisfy our original equation. Okay, so you can see that it's very similar to the differential equation case. It's just got some minor differences. So let's do another one with a slightly different non-homogeneity or inhomogeneity. Xk, so we're using a different dependent variable here, just as an exercise, minus xk minus 1. Again, this is first order, so k is the highest. So let me write this down, equals 2k. So k is the highest order, so it's k minus 1, so this first order. And we could write this as xk plus 1 minus xk, just by shifting this, but let's leave it as is for now. Okay. So we have lambda minus 1 equals 0, so lambda is our only eigenvalue and is equal to 1. So our general solution for xk is going to be equal to some constant times 1 to the power of k. Right? And for our particular solution, we're going to have so 1 to the power of k is a constant. Okay, so the general solution is just a constant. So looking at the right hand side, let's say our particular solution is xk equals some constant times k. Right? Now if we now we need to compute xk minus 1, so pxk minus 1 is going to be equal to ak minus a. Right? So I just substitute wherever a k, I had k minus 1 multiplied out. If I substitute these two equations, into the original equation, what do I get? Well, I get that AK minus AK plus A is equal to 2K. So these terms are going to cancel. I get a constant is equal to 2 times K, where K is our independent variable. So I can't choose a constant value that's going to match the coefficient of K. Right? So I know I'm in trouble. So what do? Well, I do what I always do, and I add in another K. Right? So I multiply by K, and I have a K squared. So let's have, we'll have 2 terms in our particular solution. So, let's move on. Yeah. So what I do is, I know that this is going to give me, this doesn't suitably capture the dynamics, because I lose my K terms, and I have a constant equal to 2K, so there's some kind of contradiction happening here. So let's consider Pxk equal to AK squared plus BK, right? And I can add a C in there as well if I want. So it's a second order polynomial, because my first order polynomial didn't work for whatever reason. Pxk minus 1 is going to be AK minus 1 squared plus B into K minus 1 plus C. Right? This is going to give me AK squared minus 2AK plus A plus BK minus B plus C. K squared minus 2AK plus 1. Yep, so that's all right. Okay, BK gives me that, minus B, that, and C. So again, substitute these back to my original equation, and I get AK squared minus 2AK plus A plus BK minus B plus C. That's for the, so this term here is going to be AK squared plus BK plus C for XK for the first term, minus the second term is going to be minus AK squared. Let's do this on a new line. So XK is going to be AK squared plus BK plus C. That's for this term here, the first term, XK. Now minus XK minus 1 is going to give me minus this whole thing here. So I'm going to say minus AK squared plus 2AK minus A minus BK plus B minus C, and this must all equal 2K. So I see my AK squared terms are going to cancel off. BK cancels with minus BK, and I have C minus C cancels, and I have 2AK minus A plus B must be equal to 2K. Right? So I know here that I have 2 equations. I know that 2A must equal to 2. So the coefficient here must match the coefficient there. And minus A plus B must equal 0. So minus A plus B must equal 0. So I have that 2A equal to 2 tells me A is equal to 1. And minus A plus B tells me that B is equal to A, so B is also equal to 1. Right? And I'll write the final solution here. So we have our general solution. So our final solution xk is going to be A times 1 to the power of k. That's from our general solution. And our particular solution is of this form. So A is 1, so it's going to be plus k squared plus, and B is 1, k, and C is 0. So it's plus 0. So this here is our final solution. Okay. And the reason why this failed is because our general solution is just a constant. Okay, and so the general solution being constant means that if we had taken our particular solution just to be bk plus c, the general solution captures this. And we saw from our experiment here that the k terms, the linear terms, cancelled each other off. So we've basically, what we're seeing is that the general solution is capturing the linear component of the particular solution. So we need to introduce a higher order term to capture a new solution. And we've always done that by multiplying that by k. And so we have a second order polynomial in k, and we see that that works out and gives us a solution. Again, you can plug this back into the original equation and verify that it works. And so the third example is very similar, and so I'm going to leave it for you to do. So the third example here is a good exercise for you to do from the notes, and hopefully you'll see you have a similar behavior and you'll get through it. Okay, so the next section is 3.4.5 on page 8, and it's solving system of difference equations. Okay, and so this is a bit tricky, so I'm going to try and work through it systematically and slowly for you to follow. So first of all, I'm going to do is I'm going to write down the equation in vector form. So xk plus 1, yk plus 1 on the left-hand side equals, and it's exactly like I did for the previous for differential equations. I write it down in difference in vector form, and I have xk, yk. Right. So I've just taken this equation, moved everything to the right except for the xk plus 1 and yk plus 1. Leave that on the left. Everything to the right, and I get this vector form. So I'm going to call this matrix A just as convention. So the first thing I want to do, or the goal of what I want to do, is I want to decompose A. Or essentially what I want to do is I want us to decouple these equations, right? Because I know I can solve one first order difference equation. And so if I could solve these two things independently, then I could solve x and solve y as separate problems. Then I know I can do that. Okay. And so what I'm going to do is try and decompose A, or write a matrix A, such that I get two decoupled first order equations. Right. So xk by itself and yk by itself. So how do I do that? Well, it all comes down to eigenvalues and eigenvectors. Okay, so I know that I can write A in this form. So P, this is a capital lambda, and P inverse. Okay, and P is just the matrix of eigenvalues, v11, v12, v21, and v22, as we saw before, right? The inverse of this we can calculate as you did in maths, and probably in the beginning there with Professor Harley. And lambda is the matrix with eigenvalues on the diagonal. Okay. So let's get to it. So calculating the eigenvalues, what do? We know that the determinant of A minus lambda I equal to 0 will give us the eigenvalue. So I calculate the determinant 4 minus lambda, 1 minus lambda, so A times D minus B times C, so it's plus 2 equals 0. And I get lambda squared minus 1 minus 4 is going to be minus 5 lambda. Plus 4 plus 2 gives me plus 6 equals 0. So lambda is going to be 3 times 2 and minus 3 minus 2. So minus 3 minus 2 is minus 5, minus 3 times minus 2 is minus 6. Okay, that's good. So lambda 1, I just want to get this right way around. Let lambda 1 be 3 and lambda 2 be 2. Okay. So, calculating the corresponding eigenvectors, I know that A minus lambda 1 times v1, which I don't know, equal to 0. I can solve this equation, so lambda 1I, sorry. I can solve this equation for v1 for the first column of the eigen. So this column here, v11 and v12. And I get here, so in vector form, I get 4 minus 3 minus 1, 2, and then 1 minus 3. v11, v12 equals 0, 0. So 4 minus 3 gives me 1, 1 minus 3 gives me minus 2. So I have, I'll write it again as 4 minus 3 is 1, minus 1, 2, 1 minus 3 gives me minus 2, v11, v12 equals 0, 0. You can see that if I multiply the top row by 2, I get the bottom row, so these two rows are linearly dependent, as you would have seen in algebra. And this is good news because we expect them to be linearly dependent, so there are infinitely many eigenvectors we can choose. So if I write out the top row, I get 1 times v11 minus v12 equals 0. Pick anything I want for v1, solve for v2, so this just means that v12 is equal to v11. So my vector, if I let v11 be 1, v12 is also 1, and I get the eigenvector v11. So v11 is 1, v12 is 1. Okay? And similarly, if I do the same thing for the second eigenvector, I get 4 minus 2 is going to be 2, minus 1, 2, 1, minus 2 is going to be minus 1, v2, 1, v2, 2 equals 0, 0, right? So this is just the matrix A minus lambda 2 times the identity matrix. So I just subtract the eigenvalues on the diagonal. Solve for v22 and v21. You can see the rows are the same, so they're linearly dependent. 2 times v21 minus v22 equals 0. So 2v21 minus v22 equals 0. This tells me that v22 is equal to 2v21. So my second eigenvector is, pick anything I want for v21, calculate v22. So I'm going to say this is 1 and that's 2. Okay. So my P matrix, P, is 1, 1. So this is v1 on the first row or first column, and v2 is going to be 1, 2. This is my P matrix. Okay. So if I go back to my original decomposition, what I'm looking for, I now have P. I know what lambda is, so I'll write lambda down here. I know that capital lambda is 3002. So lambda 1, lambda 2, so the first eigenvalue on the top left, second eigenvalue bottom right. And now I just need to calculate P inverse. And P inverse is... okay, sorry about that. So P inverse is 1 over the determinant, and then I just swap the diagonals elements and negate the off diagonal elements. Right, so it's obviously just for a 2 by 2. So what is this? 1 over a times d is 1 times 2 minus 1 is going to be 1. Right, so the determinant of this is 1 times 2 minus 1 times 1 is going to be 1. So 1 over 1 is just 1. And the matrix is then just 2 minus 1 minus 1, 1. So I swap the diagonal elements. So d goes there, d goes here, a goes there, and then minus b and minus c. Okay. So I now have all the elements I need. I have all the components I need to decompose my matrix A into these terms. Okay. So what do we do? So let's consider our equation in matrix form, right? So we have the unknown solution at k plus 1 is equal to this matrix A at k, right? So this is a vector, this is a matrix, this is a vector. And I know that A is equal to P lambda P inverse times xk, right? If I left multiply both sides by P inverse, so I left multiply both sides of the equation with P inverse. I know that P inverse times P is just the identity matrix by definition. And I get P inverse xk plus 1 on the left hand side. The P inverse P here goes to the identity matrix, and I'm left with just lambda P inverse xk. Right? Now, if you're looking ahead, you might notice that this here and this here look very similar. So I have P inverse times my unknown solution. and lambda is diagonal, a diagonal matrix, and this is exactly what we want. So I'm going to say let zk, so a new variable, equal p inverse times xk. And what I have is zk plus 1 from the left hand side equal to this matrix lambda, which I'll write out as 3, 0, 0, 2, which we know from before, times p inverse xk, which is just going to be zk. Right? Or, being explicit, I can write this as, say, x bar k plus 1, y bar x k plus 1 equals 3, 0, 0, 2, x bar k and y bar k. So where x bar is just the mapping from, it's just basically the components of z, where x is in x. So xk is equal to xk, yk, and then zk is these new variables. Okay. And we can see here that the top equation is now independent from the bottom equation, right? So xk plus 1 equals 3xk. So we have two different equations. Xk plus 1 equals 3xk. Doesn't have any y's in it, so we can solve this very easily. And then y bar k plus 1 is equal to 2 y bar k. We can solve that very easily. Okay. So the first order linear difference equation, we then know that xk tilde is equal to some constant, I won't use that, I'll use, say, c1 times the eigenvalue here is going to be 3. If I take that across, lambda minus 3, yep, so it's going to be 3 to the power of k. And similarly, y tilde k equals c2. Take that across, lambda minus 2 is going to give me 2 to the k. Right? So I now have the solutions here, and I have this relationship here. Okay? So I know that x tilde k, y tilde k is equal to p inverse, which was, sorry, I can't remember offhand. 2 minus 1 minus 1, 1 times xk, yk. Right? We have this, we don't have this, so what we actually want is to write down if zk is equal to p inverse xk, then xk is equal to, I just left multiply by p, and I get xk is equal to p zk. Right? And we do that, and we get that x k yk is equal to 1 1 1 2 times c1 3 to the k, c2 2 to the k. Multiply this out, I get xk is equal to c1 3 to the k plus c2 2 to the k, so that row by that column, and then yk is equal to c1 3 to the k plus 2c2 2 to the k. And that's our solution. Right? So hopefully that makes sense. I know it's a bit tedious, but it's all in the notes, and it's all in the note solutions. And hopefully you can work through it slowly, and this makes sense. So essentially all we've done is taken our matrix form here, xk, a, xk. We've written it in this decomposed form, right? So P is the eigenvector matrix, lambda is the eigenvalues, and P inverse is the inverse matrix to be calculated. Okay. What this allows us to do is write it in this form of zk equals a diagonal matrix, which decouples the systems, zk. We can then solve them individually, and we get this here. This mapping will map us back to the final solution. Okay, so this is just xk equals p, this is the matrix P, times zk, which is the solution we found in over here. Okay, so the next part of the notes talks about the direct method. And the direct method, all it is basically writing down the terms in the series that come about and seeing if we can find a pattern. So the first example is yk equals 2yk minus 1. Okay, and we can solve this using the regular method. So take it across, calculate the characteristic equation, write down the general solution. Okay, and what we're saying here is we're saying we know what y naught is. So when k is equal to 0, y naught is our initial condition. So y naught, so y1 is going to be equal to 2y naught. Okay, y2 is equal to 2y1, which is equal to, substitute this into here, I get 2 times 2 is 2 to the 2 y naught. Okay, y3 is equal to 2y2, which is equal to 2 times this thing here, so it's going to be 2 to the 3 y naught. So the solution that I'm looking for is y to the k equals 2. So I see here y1 is equal to 2 to the 1 times y naught, y2 is equal to 2 to the 2 times y naught, y3 is equal to 2 to the 3 times y naught, so this is yk is going to be equal to 2 to the k times y naught. And this is exactly the solution you get if you use calculate the characteristic equation and then write down the general solution that way. Okay, so this is an easy example, and you can see how this comes about. One kind of tip is try not to write out this is 4 and this is 8. So try not to kind of simplify it as it were, because that tends to cloud the pattern, right? If I write it as 2 to the 2 instead of 4, I can see that this 2 matches the exponent here, and 2 to the 3 instead of 8, I can see that this k, or this 3 here, matches the exponent, and that allows me to see that k will match the exponent there. So that kind of helps to match the patterns. Okay, so that's example 1. Example 2 is a little bit trickier. So yk plus 1 is equal to k plus 1 times yk, and given our initial condition y naught. So y1 is equal to, k is still 0, y1, 0 plus 1 is 1 times y0. Okay. y2 is equal to, so k is now equal to 1, k equal to 1, 1 plus 1 is 2, 1 plus 1 is 2, so I have 2 times y1, which is equal to 2 times y0. K equal to 2, so k plus 1 is 3, k plus 1 is 3 times y2, this is equal to 3 times 2 times y0. Okay, and again, I'm not writing this as 6, I'm writing this as 3 times 2. Let's try one more, hopefully it makes it a bit clearer. So this is k equals 3, this is 3 plus 1 is 4 times y3 is equal to 4 times this is 4 times 3 times 2 times y0. So the general solution is then equal to k, so 4 times 3 times 2 is 4 factorial, so it's going to be k factorial times y0. Right? So 3 is 3 times 2 times 1 times y0. 4 is 4 times 3 times 2 times 1 times y0. So this is 4 factorial, it's 3 factorial, it's 2 factorial, and 1 factorial. So yk, the general form is k factorial times y0. So hopefully that makes things a bit clearer, a bit easier. And then the next section talks about solving these things using a computer. And so what I'm going to do is show you on my iPad here. So what are we doing? We're going chapter 3. Essentially what we do for the computer method is we write down what we essentially do the direct method and record the numbers. Okay, so Let's zoom in here a little bit. Okay. So given an initial condition here, y0, y1 equals 1. So if I have y0 here, y1 here, I can calculate y2. Okay, and I'll write it down. So y0 is 1, y1 is 1, and y2 is calculated to be 0. I then say, well, say y1 is this, so y1 is 1, y2 is 0, what's y3? So I increment k, and I get minus 2. I then increment k again, I say, well, y2, y3, what's y4? I solve for y4, and I plug it in. And in doing this, I can calculate the series that satisfies the differential equation given some initial condition. So the important point to note here is that the computer method can only be used when we have an initial condition with a number. So we can only compute the new numbers by substituting in the old numbers. Okay, and we solve this thing iteratively. So we have y0, y1 calculate y2. Then we have y1, y2 calculate y3. Then we have y2, y3 calculate y4, and so on and so forth. And in this case, and I urge you to go and try and implement this in Mathematica, I've used this thing called rsolve or recurrence table, which you'll see in the lab, lab 4, I think, or lab 3, and I just plotted the solution. You can see it's these stepwise functions because it's discrete, so I've just connected the dots, and it's this kind of growing oscillations which we expected to see. Okay. Similarly for a system, you'll be pleased to know the system's a bit easier for the computer method. So I have x0 and y0. I substitute x0 and y0 into the equation. I calculate x1 and y1. Then I have x1. I plug x1 and y1 into the equations on the right-hand side. Calculate x2 and y2, and so on and so forth. And what I get is this thing here. So the blue line is x, and the orange line is y. Okay. You can calculate this by hand. You can code it up by hand using for loops, that kind of thing. But Mathematica has this nice function called a recurrence table, where you define your recurrence relation. So you define how the equation is defined, and it'll update accordingly. Okay. So that appears to be the end of the chapter, if I'm not mistaken. No. Yes. So so the end of the chapter talks about writing a computer program in MATLAB. I don't want to use MATLAB. I want you to use Mathematica. Hopefully, it's a bit easier. And you'll see that the computer method is really just a numerical method, and it's really just a series update. So hopefully this makes sense. Tackle the tuts. You should be able to do all of tut 3 now. Tackle the tuts. If you see a nonlinear equation, you must use the direct method. So try and do the patterns, find the pattern. The eigenvalue method won't work. Calculating eigenvalues won't work. All right, good luck, and hope this helps.